Welcome to C Programming Lecture 10. In this lecture we will look into how to write programmer-defined functions in C programming language that can help to write C programs that require some calculation or process needs to be performed at different stages of the program, with different parametric values. C programming language is all about writing functions. Any C program will have minimum one function called the main function. Main function is the boss of the C program and it can have workers called functions. As the first example, we will look into the procedure of how to write a programmer-defined function that can perform the addition of two integers passed on as parameters or arguments in the function will return the added up integer value to the program location, where the function has been invoked. We know the usage of standard library functions available in header files like math.h. For example, sqrt function in math.h can be invoked by passing on a parameter and it will return a double precision value. Note that sqrt is the function name. One parameter or argument is passed on to this function and the function will return a double precision value. In programmer-defined function as well we need to have a function name, number of parameters or arguments to be passed on to the function, and the type of return value. In this C program, we write a programmer-defined function named int_add, two integers parameters, namely x and y that are to be added and the function will return that integer value. Line 5 is the function prototype. That is to be written with the type of the returned value followed by the function name followed by the types and names of the parameters separated by commas enclosed within parentheses and finally a semicolon. Definition of this function named int_add is written after the main function from lines 22 to 25. In this C program, line 5 is the prototype of the function int_add written outside any function as a global function. So, this function is available to be invoked from any functions written in this program. In this program there are only two functions, namely the main function and the int_add function itself. If required, a function can be invoked from within itself. This will become a recursive function call. Example of recursive calling of a function will be looked into in later lecture. Lines 22 to 25 are the lines written for the definition of the int_add function. Compare the prototype of the int_add function in line 5 with the definition written in lines 22 to 25. Semicolon at the end of the int_add function prototype in line 5 is replaced with the scope of the function enclosed within braces in the int_add function definition written in lines 22 to 25. Line 7 is the first line of the main function, which is the boss of the C program. Main function does not take any parameters, so either void or nothing mentioned within the parentheses. Return type of the main function is an integer. In line 18, integer 0 is returned for the successful termination of this C program. Scope of the main function from lines 9 to 18 are enclosed within braces. In C programs, the respective scope of all functions are to be enclosed within braces. Line 22 is the first line of the definition of the int_add function, which can be invoked with two integer parameters. These two integer parameters, namely x and y, are declared as int and enclosed within the parentheses. This is in a sense that these two integer type variables are declared for this function and available for further processes in the scope of this int_add function. Return type of the int_add function is an integer. In line 24, integer value computed as x plus y is returned as the integer value to the place where this int_add function is invoked. Scope of the int_add function is the single line 24 enclosed within the opening brace in line 23 and closing brace in line 25. Note that one tab indent spacing is maintained for line 24 for the structured C programming. In the main function, two integers are received through the keyboard and stored in the memory locations of variables a and b. Line 14 is an assignment statement that assigns the integer value, returned by the int_add function, to the integer variable c. Right-hand side of the assignment statement in line 14 invokes the int_add function with two integer values a and b. To invoke a programmer-defined function, we have to write the function name followed by the required number of parameters values, same as the number of parameters written in the definition of the function, within the parentheses, separated by commas. The values of the integer variables a and b through the function call are respectively copied to the integers variables x and y in the int_add function in line 22. In the function as written in line 24, integer value computed as x plus y is returned as the integer value to the right-hand side of the assignment statement in line 14, where the int_add function is invoked. Thus, the added up value of variables a and b, computed and returned by the int_add function, will be assigned to the left-hand side variable c. As the values of the integer variables a and b through the function call are respectively copied to the integers variables x and y in the int_add function, this type of function invoke is termed as call by value. Another type of function invoke called call by reference is also available using pointers that are through the memory address and its contents. In later lecture, we will look into calling a function by reference. In the main function after line 14, variable c value is available for any further processes. As this is an example C program written for the understanding of the basics of function, the c value is displayed on the monitor, using the printf statement in line 16 and the program is ended. Display of the execution of the exe file. Input two integer values and final output are shown in the inset window. In the last lecture we have written a C program to convert the input resistor or inductor or capacitor value to its higher or lower order units and displayed the converted device value with its appropriate units. In many other programs that are written for various computations, designing and data processing of electrical signals and/or systems, this kind of device value conversion and processing of the appropriate units might be needed. If we write the device value conversion part as a function, it will become quite handy to call it whenever required. Let us amend the C program to separate the device value conversion part as a function that can be called with necessary parameters for the conversion to be performed. And after the conversion process, the converted value, number of decimal point positions moved to the left or right, and the appropriate higher or lower units are returned to the place where the function is invoked. Line 17 is written for the prototype of the function named valUni that receives two values of type double and character and return a structure of type scale units. ValUni function can be invoked with the device value in double precision and a character that represents a device type as either resistor or inductor or capacitor. Functions in C programming language can return only one quantity of the specified type. In the valUni function a structure type is returned that indirectly returns three quantities, namely the converted value, number of decimal point positions moved to the left or right, and the appropriate higher or lower units. The definition for the function valUni has to be written after the main function to process the conversion of the device value and the appropriate higher or lower order units, by moving the decimal point position to the left or right, if necessary depending on the value range. The conversion part of the code written in the previous C program has to be separated and to be used as the scope of the valUni function. In the main function, in lines 21 to 23, only those quantities required within the main function are declared. Those quantities required for the conversion are not required here in the main function and are to be declared locally in the valUni function. In the main function, using line 29 scanf statement within the dual repetition statement, one among the characters RLC input through the keyboard is stored in the memory location of the variable named type. In the main function, using line 56 scanf statement within the dual repetition statement, the positive device value input through the keyboard is stored in the memory location of vu.val. In this C program, the main function ends with a closing brace in line 71. Line 76 is the first line of the definition of the valUni function, which written in the same way as its prototype in line 17, without the semicolon at the end of the line. The scope of the function valUni to perform the device value conversion and processing of the appropriate units starts from line 78. Which is after the opening brace in line 77. Line 65 is an assignment statement that assigns the structure of type scale units returned by the valUni function to the structure of type scale units VU. Right-hand side of the assignment statement in line 65 invokes the valUni function with the double value vu.val and character value type. The double value vu.val and character value type through the function call are respectively copied to the val and type parameters in the valUni function in line 76. In the function after the conversion process, converted value, number of places decimal point moved and the corresponding units are all together as a structure of type scale units is returned to the right hand side of the assignment statement in line 65, where the valUni function is invoked. Thus, the returned structure quantity by the valUni function will be assigned to the left hand side structure VU. Note that within every function required quantities are locally declared within the respective function. Any quantity declared within a function is available only to that function and has no connection to other functions in the same C program. For example, both in the main function and also in the valUni function, character variable named type and structure of type scale units named VU are locally declared. Even though the names are exactly same, they are not at all connected. Only because of the invoking of valUni function in the right hand side of line 65 assignment statement, the character value of variable type of the main function will be copied to the character variable type parameter in the valUni function. In the first line of the definition of the valUni function, in line 76, through required parameters enclosed within parentheses, some quantities for the valUni function gets declared. In the valUni function, in line 78 to 81, only those remaining quantities required within the valUni function are declared. Through line 65 valUni function call with vu.val as a passing value from the main function, copied to the declared val parameter of the valUni function in line 76. And this variable val value is used to initiate the vu.val declared within the structure in valUni function in line 78. Thus, the device value and type passed on to the valUni function are locally available in the vu.val and type variables for the conversion process by moving the decimal point and to compose the corresponding higher or suborder units. Line 76 to 145 are written for the definition of the valUni function to perform the conversion process and return the structure of type scale units to line 65. Where the valUni function was invoked. The statements written for the conversion process co-chunk part of the previous lecture C program is separated and used as the scope of the valUni function. In the valUni function after the conversion process, converted value, number of places decimal point moved and the corresponding units are all available together as a structure named VU. as written in line 144. This structure VU is returned to the right-hand side of the assignment statement in line 65, where the ValueUni function was invoked. In the main function after line 65, structure VU is available for any further processes. The converted value of the device with its units is displayed on the monitor, using the printf statement, and line 68 in the main function is ended. Display of the execution of the exe file, input device type and value, and final output are shown in the inset window. In C programming language, like the standard library header files available as separate files with .h file extension, programmer-defined functions can also be written separately and included in other C source codes. To get an idea on how this can be done, let us write the ValueUni function as a separate file with a suitable file name and file extension as .h. For simplicity and to avoid any ambiguity, it is better to have the file name same as the function name. So, this file full name is chosen as ValueUni.h. With the statements written for the ValueUni function, there is no requirement of any standard header file, and hence we have not included any. In most cases, the .c source code that includes programmer-defined separate .h function file might have all standard header library files included. In case of any header file specifically needed because of the statements written within the programmer-defined separate .h function file, then that has to be included here. Structure scale units definition is needed here, as structure named VU is declared of this type and it is returned to the place this function is invoked from other .c programs. Also note that this structure scale units definition and corresponding type definition in line 12 are written in the global area, before the definition of the ValueUni function in line 15, as structure of type scale units is needed in other .c programs. There are no changes in the definition of the ValueUni function written in the programmer-defined function file named ValueUni.h. This C program is same as the lec10 function 2.c program, with a replacement of ValueUni function definition as .h header file inclusion in the preprocessor directive. Line 5 is written to include the programmer-defined function header file ValueUni.h. Note the difference between the standard library header file included in lines 3 and 4 with the programmer-defined header file included in line 5. In line 5, the programmer-defined function header file ValueUni.h is enclosed within double quotes after the keyword include. As the ValueUni.h file is made available in the same folder as with this lec10 function 3.c source file in the computer secondary memory, no file path is mentioned. If the header file is stored in a different folder that of the .c source code file, then the file path of the header file as well need to be included with the .h header file. While linking, all the lines available in the programmer-defined function header file ValueUni.h will be included here. So, all the preprocessor directive lines written before the inclusion of the programmer-defined function header file are available to the code chunk written in the .h programmer-defined function file. Thus the stdio.h and math.h header files included in lines 3 and 4 are available to the code chunk written in ValueUni.h file. Similarly, the code chunk written in ValueUni.h file is available to the rest of the statements written in this lec10 function 3.c program. Scale unit structure is defined and its type definition as scale units are written in the global area of the ValueUni.h file. So, in the main function here in line 9, VU is declared as a structure of type scale units without need for any structure definition written here. Thus, while developing software that has multiple files, extra care must be taken on what code chunk has to be written in which file and at what area within every file. No changes in the main function code chunk written here compared to the previous C program file named lec10 function2.c. Thus, the valueuni.h function file is written as a standalone programmer-defined header file that can be used by any other C program that requires RLC device value conversion and composing of the corresponding higher or lower order units. In large software developments, team members are usually given with tasks designed by the team manager to develop different parts of the specification of the project code. Individual team member will coordinate with other team members to develop the code for their assigned task as function source code files in such a way that finally all files can be controlled by one boss source code, namely the main function in the C programming language environment. Let us amend the C program written in the file named lec08 while statement2.c to make use of valueuni.h function file and also to facilitate to take input values for the load RLC in their respective higher or lower order units. This C program is the modified version of the lec08 while statement2.c program written for the calculation of the equivalent impedance of all the loads connected to the mains AC power supply and to compute either the compensating capacitance or inductance value to remove the reactive power consumed. Let us look into the details of the modifications made in the C program because of the inclusion of valueuni.header file and processing the input load RLC values in the higher or lower order units to their respective base units values for impedances calculations, and finally displaying the compensating inductance or capacitance in their respective higher or lower order units. Line 5 is written to include the programmer-defined function header file valueuni.h. As the valueuni.h file is made available in the same folder as with this lec10 function4.c source file, in the computer secondary memory, no file path is mentioned. If the header file is stored in a different folder that of the .c source code file, then the file path of the header file as well need to be included with the .h header file. Line 17 is written for the prototype of the function named rescale that takes a character value and returns a double value. This function is written to process the rescale factor for the input load RLC values in any higher or lower order units to their respective base units values for impedances calculations. Character corresponding to the load RLC units in their respective higher or lower order is input through the keyboard, and that character is passed on to this rescale function. Let us look into the definition of this rescale function on how it returns the appropriate double rescale factor to scale the input load RLC values to their respective base units. Just after the end of the main function, lines 256 to 297 are written for the definition of the function named rescale that takes a character value and returns a double value. Single switch statement that checks the character value passed on to the parameter named units is written for the scope of this rescale function. Depending on the character value, corresponding double value is returned as the scale factor to the location where this rescale function has been invoked. Within the switch statement, variable units cases are checked for the characters MUNP for the subunits milli, micro, nano, pico to return the scale factors as 10 raised to the power minus 3, 10 raised to the power minus 6, 10 raised to the power minus 9, 10 raised to the power minus 12. As no rescaling required for the base units, variable units cases are checked for the characters OHF for the base units ohm, Henry, farad to return the scale factor as 10 raised to the power 0. Variable units cases are checked for the characters kmgt for the higher units kilo, mega, gigatera to return the scale factors as 10 raised to the power 3, 10 raised to the power 6, 10 raised to the power 9, 10 raised to the power 12. Within the switch statement, For every case checked for the unit's character, the corresponding double scale factor is obtained through the POW function available in the math.h library header file. Note that all these cases double scale factor is returned to the location where this rescale function is invoked with as many returned statements as the number of checked cases. Instead of so many return statements, the other possible way could be declaring a local double type variable in the beginning of this function between lines 257 and 258. And all the return statements within every case scope are replaced with assignment statements to assign the scale factor to the double type variable. Finally, after the switch statement between lines 296 and 297, single return statement to return the double type variable value is to be written. If the function is written this way, it will increase the number of code lines and also 8 bytes of extra memory required, and it will increase the processing time a bit more. It might look like 8 bytes is very small amount of RAM memory, and the data communication between the microprocessor to the RAM memory to access the double variable value is going to be only few times. But we should always keep the idea that a function can be called many times due to large computation, and in case of processing huge data and continuous monitoring of signals and systems can lead to big amount of memory and processing time. So, it is always better to develop an optimized code with respect to cost functions like memory resource, processing time, and data communication speed and bandwidth. If required, this definition of the function rescale can be separated and saved as a programmer-defined.h function file and included in the header like the value_uni.h included in line 5. Lines 24 and 25 are written for the declaration of the structures of type scale units, which is defined in the value_uni.h function file. Array of structures declared in line 24 are for the conversion of the input load RLC values for the display with the appropriate units. Structures declared in line 25 are for the conversion of the calculated compensating inductance or capacitance value for the display with the appropriate units. Lines 31 to 39 do while statement that includes the scanf statement and line 33 are written with the appropriate checking condition within parentheses in line 39 to accept only positive value for the AC signal frequency. Note that one blank space is included before the %LF identifier in the scanf statement to avoid the display of the next printf statement message twice on the monitor. Lines 47 to 55 do while statement that includes the scanf statement and line 49 are written with the appropriate checking condition within parentheses in line 55 to accept only positive value for the load resistance or -1 if no load connected. Input load resistance value is stored in the memory location of the first element of the double type array R. Line 61 to 69 do while statement that includes the scanf statement in line 63 are written with the appropriate checking condition within parentheses in line 69 to accept only a character 1 among O or K or M for the load resistance units. Input load resistance units character is stored in the memory location of the character variable units. Line 72 is an arithmetic assignment statement that rescales the first element of the R array with the double scale factor returned by the rescale function, which is invoked with the input load resistance units character value. Thus the input load resistance value in R of 0 is rescaled to the base unit's ohm value that can be used for the impedances calculations. Line 79 to 87 do while statement that includes the scanf statement and line 81 are written with the appropriate checking condition within parentheses in line 87 to accept only positive value for the load inductance. Input load inductance value is stored in the memory location of the appropriate element of the double type array L. Lines 91 to 101. Do while statement that includes the scanf statement in line 93 are written with the appropriate checking condition within parentheses in lines 100 and 101 to accept only a character 1 among H or M or U, or N or P for the load inductance units. Input load inductance units character is stored in the memory location of the character variable units. Line 104 is an arithmetic assignment statement that rescales the appropriate element of the L array with the double scale factor returned by the rescale function, which is invoked with the input load inductance units character value. Thus the input load inductance value in L of n is rescaled to the base units Henry value that can be used for the impedances calculations. Lines 108 to 116. Do while statement that includes the scanf statement and line 110 are written with the appropriate checking condition within parentheses in line 116 to accept only positive value for the load capacitance. Input load capacitance value is stored in the memory location of the appropriate element of the double type array C. Lines 120 to 130. Do while statement that includes the scanf statement in line 122 are written with the appropriate checking condition within parentheses in lines 129 and 130 to accept only a character 1 among F or M or U, or N or P for the load capacitance units. Input load capacitance units character is stored in the memory location of the character variable units. Line 133 is an arithmetic assignment statement that rescales the appropriate element of the C array with the double scale factor returned by the rescale function, which is invoked with the input load capacitance units character value. Thus the input load capacitance value in a C of n is rescaled to the base units farad value that can be used for the impedances calculations. Lines 155 to 163. Do while statement that includes the scanf statement and line 157 are written with the appropriate checking condition within parentheses in line 163 to accept only positive value for the load resistance or -1 if no load connected. Input load resistance value is stored in the memory location of the appropriate element of the double type array R. Lines 169 to 177. Do while statement that includes the scanf statement in line 171 are written with the appropriate checking condition within parentheses in line 177 to accept only a character 1 among O or K or M for the load resistance units. Input load resistance units character is stored in the memory location of the character variable units. Line 180 is an arithmetic assignment statement that rescales the appropriate element of the R array with the double scale factor returned by the rescale function, which is invoked with the input load resistance units character value. Thus the input load resistance value in R of n is rescaled to the base units ohm value that can be used for the impedances calculations. Lines 197 to 199 are assignment statements that assign the appropriate element of the structure arrays with the VU structure returned by the value uni function, which is invoked with the appropriate load value and the corresponding device type character. Left-hand side structure arrays quantities will have the converted device values and the corresponding higher or lower order units. These quantities can then be appropriately used in the printf statement for the display on the monitor. In lines 204, 216, 220, and 226 printf statements, %E identifier is used to display the real and imaginary parts of the impedances in scientific notation. Lines 237 and 244 are assignment statements that assign the appropriate structure with the VU structure returned by the value uni function, which is invoked with the compensating inductance value and character L in line 237 and compensating capacitance value and character C in line 244. Left-hand side structure quantities will have the converted device values and the corresponding higher or lower order units. These quantities can then be appropriately used in the printf statement for the display on the monitor. Display of the execution of the exe file. Input AC supply frequency. 2 loads RLC values and units. -1 sentinel value and final output are shown in the inset window. All the C programs examples discussed in this lecture are provided to learn about functions called by value. Try to write C programs yourself to get more practice, experience and confidence in coding computer programs. In the next lecture, we will see how recursive call-off functions, pointers and functions called by reference are useful to write C programs that can solve scientific and engineering problems.